Hello everyone and welcome back to the IBPS SO Professional Knowledge series. In video 1, we covered generations of computers, number systems, data units. Today, we go one level deeper. What's actually happening inside the CPU and what happens the moment you press the power button. So, two topics today, CPU architecture and the booting process. Almost every computer you have ever used follows an architecture proposed by John von Neumann in 1945 called the von Neumann architecture or the stored program concept. The core idea is both program instructions and data are stored together in the same memory and the CPU fetches them one at a time to execute. Before this, early computers had to be physically rewired to run a different program. Exam hook. If you see a question asking which architecture stores program and data in the same memory, the answer is always von Neumann. There is a contrasting architecture called Harvard architecture, which uses separate memory for instructions and data. IBPS has tested this contrast directly. So remember, von Neumann is equals to shared memory and Harvard is separate memory. Now, key components list. CPU, central processing unit, the brain, does the actual processing. Memory unit, stores both instructions and data. Input and output devices, how data enters and leaves the system. System bus, the pathway connecting all of the above. Now, CPU is made up of ALU, CU, and registers. What is ALU? Arithmetic logic unit. It performs all arithmetic operations. It performs all logical operations. Second, control unit. It does not perform calculations itself. It directs and coordinates the activity of the entire CPU. It tells the ALU when to compute, tells memory when to fetch store, manages the flow of data between components. Think of the CU as the traffic controller and the ALU as the calculator. This distinction, ALU calculates, CU controls, should be remembered clearly. Registers are small, extremely fast storage location inside the CPU itself. It is much faster than RAM, but very limited in number and size. IBPS tests these registers the most. PC is program counter. It holds the address of the next instruction to be executed. IR is the instruction register. It holds the instruction currently being executed. A simple way to remember the distinction between PC and IR is PC points to what's coming next. IR holds what's happening right now. MAR is memory address register. It holds the address of the memory location to be accessed. And MBR is memory buffer register. It holds the data being transferred to or from memory. MAR and MBR always work as a pair. MAR says where in memory to look and MBR carries what was found there or what is being written. Accumulator. It stores the intermediate results of arithmetic and logic operations. The system bus. A bus is a set of physical wires that carries information between components. There are three types. First, data bus. It carries actual data instructions. It is bidirectional. Second, address bus. It carries memory addresses. It is unidirectional. Third is control bus. It carries control signals like read, write, clock signals. It is also bidirectional. Exam trap to watch for. The address bus is unidirectional. The CPU tells memory where to go, but memory does not take back on the same bus. Remember this. The data bus is bidirectional. Data flows both into and out of the CPU. The instruction cycle, often abbreviated as the fetch, decode, and execute cycle. If you see this phrase in a question, know that it is always these three steps, always in this order, and it repeats continuously. This is fundamentally how a CPU runs any program at all. So first is fetch. The CPU uses the program counter to find the address of the next instruction. We have already seen this in registers that program counter holds address of next instruction. That address goes into the MAR. MAR holds the address of memory location to be accessed. The instruction itself is retrieved from memory into the MBR, then moved into the IR. IR holds the instruction being executed. So once the instruction is fetched successfully, the program counter is incremented to point to the next instruction. So we have successfully fetched the instruction, then decoding happens. The control unit interprets the instruction sitting in the IR. It figures out what operation it represents and what data it needs. So after decoding, then execution happens. The ALU, for arithmetic and logic operations or other CPU components, carry out the actual operation. Results may be stored back in a register or in memory. Now, two philosophies for designing a CPU instruction. First is RISC. It is designed to execute a small, simple set of instructions very quickly. The main idea is that simple instructions can be executed in fewer clock cycles, making the processor faster and more efficient. Example, ARM processors. Second is CISC. It uses a large set of complex instructions where a single instruction can perform a multi-step operation. Each instruction may take multiple clock cycles. More complex hardware but fewer instructions. Example, Intel and AMD processors. A quick comparison. Remember, instruction set in RISC, small simple. CISC, large and complex. Cycles per instruction in RISC, usually one. In CISC, multiple. RISC has simple hardware, CISC more complex. Examples, ARM, there, Intel and AMD. Common use cases, mobile devices, power efficient systems, and CISC, desktop, laptop, servers. Now, the second topic, booting process, meaning process of starting a computer. There are two types of boot. First is cold boot and second is warm boot. Cold boot means your computer was completely powered off and you are turning it on. And warm boot, it was already on but you have restarted it. Cold boot is also called hard boot. Warm boot is called soft boot or restart. Hardware check in cold boot, full post. It checks all hardware. And in warm boot, usually skips or shortens post. Cold boot, pressing the physical power button. Warm boot, generally restart command. Cold boot, it is slower because full hardware initialization. And warm boot is faster. Simple way to remember it. Cold means the machine was cold, that is no power at all before you started it. And warm, it was already warm, that is it was already powered on, you have just restarted. So this is how you can remember it. Now, if IBPS asks which type of boot involves switching on the computer from a completely powered off state, that's always cold boot. The boot sequence. Here's what actually happens between pressing the power button and seeing your desktop. First is power on. Power supply sends electricity to all components. Second is BIOS, yeah, UEFI initialization. BIOS means basic input output system, or its modern replacement is UEFI, which is Unified Extensible Firmware Interface. It is a firmware stored on a chip on the motherboard. So it is the very first software that runs before any operating system loads. Third is post. So BIOS or UEFI runs post, which checks that essential hardware, RAM, keyboard, storage drives, graphics is present and functioning. If post fails, you typically hear beep codes or see an error screen before the OS even attempts to load. This is a classic sign the problem is hardware, not software. Fourth, bootloader execution. Once post passes, BIOS or UEFI hands control to the bootloader, a small program whose only job is to locate and load the operating system. Example, Windows uses a bootloader called Windows Boot Manager. Linux commonly uses grub. Fifth, OS loads into the RAM. The bootloader loads the OS kernel into RAM. The OS takes over, initializes drivers and services, and eventually presents you with the login screen or desktop. Quick note, BIOS is the oldest standard, has a text-based interface and can typically only boot from drives up to 2 TB. UEFI is the modern replacement, supports larger drives, boots faster, and has a graphical interface. So that was all for this video. In next video, we will cover input, output, hardware devices, printer types, and ports. If you like the video, please press the like button, subscribe to our channel. Thank you.